So far, we have seen how to compute Khovanov homology and some related homology theories which are related to Khovanov. For example, Lie homology, annular Khovanov homology, uh, etc. And as the name suggests, I really want to introduce some homotopy theories. Let me write down what I want to introduce. I want to introduce Khovanov stable homotopy. If you're seeing this for the first time, if the word stable make you uncomfortable, you can just sweep it under the rug, keep it under the parenthesis. Think about just a homotopy theory and build upon Khovanov homology. And the way we build any homology theory is essentially first thing first, we build a chain complex. We associate the vector spaces to it. So let's do it. This is your homology. This is your homotopy. What we have in this chain complexes are objects like this, where your vector space generator, remember that your V is generated by two vector space element x plus and x minus with some relationship in between them, where x plus is getting mapped into x plus x minus plus x minus x plus, and x minus is getting mapped into x minus x minus. And the dual picture will give you the multiplication map, but for now, let's just focus one of these examples. Note that I can write this as your plus because these are my vector spaces. So essentially, to do homology theory, you need some sort of algebra in the picture. So this part is really what you're doing is using the algebra of the vector spaces to define the chain complexes. This is why you're using the algebra. And homology in theory is very algebraic. You use homological tools, you use your homological algebra to do some algebra on it. But homotopy theory, by nature, we want to talk about topological spaces to it, right? That's the nature of the subject as it is. If there is some chain complexes, homology theory involved, we talk about algebra. If there is some homotopy theory involved, we really want to talk about some topological spaces, at least if you're seeing the homotopy theory for the first time. So what we want to do is to forget this algebra structure and we remember all this information individually in terms of your objects and arrows. So still, this is your split map. Let me use the splitting here. And still you have the same map. It goes to x plus. But now we really don't want to be dependent on this algebra structure. So we want to represent this by two arrows. If this is a vector space, if this is algebra, I take summation of them. If this is some other just a set, these are just arrows. So depending on what information we want, we'll associate that information to these arrows. But for now, these are just some elements and some arrows coming out of it. Same here, some arrows. And you have missed one generator on this left-hand side, that is your x plus, which does not take any arrow. So in this side, we do have an arrow x plus 0 is getting mapped to, 0 doesn't get mapped to 0. It does get mapped to 0. It doesn't map anywhere, but whatever. Here you also have x plus, which is not an image of this map. All right. So this is your algebra structure. This is just some information. These are my objects, and these are my objects, and these are my morphism in between them. Now, what you really want to do, if you want to do some homotopy theory, as I'm saying, you really want to build a topological space out of it to introduce the word homotopy. How would you do that? The traditional tool that is available in literature that turns homology or chain complexes into some topological space, that is called Cohen-Jones-Seagal's construction. Let me tell you what it does. Cohen, Jones, Segal. Not our Cohen, Jones, some other Jones, and Segal is the famous Segal. What they did, they asked this question, given any chain complex, C dot, any chain complex, doesn't have to be a cellular chain complex, doesn't have to come from topology, algebraic chain complex. I think they do assume that it's bounded below, out of which they want to build a topological space whose cellular chain complex is this guy. So X is your topological space. Anytime I have a topological space, I can make a cellular chain complex out of it by looking at its cell decomposition, or a singular chain complex out of it. Let's not call it topological place. Let's call it a topological cellular space, like a CW complex. Yeah, to make sense of cellular chain complexes. So anytime I have this guy, I can make a cellular chain, cellular, C cellular, C cellular. This C cellular becomes chain homotopic or isomorphic to up to some isomorphism. These two are same. That's the idea. That's the idea we have. And to make sure that your CJS work, your input has to be some kind of flow category. If you, so the input here is your flow category. It takes in flow categories and spits out topological spaces. How? Sweep it under the rug. We'll see some example, but we need this guy to get some input in it. What we have is this guy. And this does look like a flow category. So this is your 0 and this is your 1. You can think of, so instead of thinking these morphisms as morphism or as arrows, you think of them as flows. A flow is a unique morphism coming from higher index to the lower index. Your index is this states, this 1, 0. If this is a square, 0, 0, 1, 0, 0, 1, 1, 1. Your states, your index of the states are 2, 1, 1, 0. Your flow comes from 2 to 1, then 1 to 0, then 2 to 0. Like that. The idea is to think of this diagram in terms of your flows. Think these objects as your objects over there, and the morphisms are dictating the flow. So let me draw exactly this diagram, 90 degrees shifted, and with the direction of the arrows on the opposite side. Let me show you how it looks like. So let me see. Yeah. So yeah. This is your X plus. This is your X minus. They are at the 0 level. This is your 0. And they are at the 1 level. At the 1 level, I have generator. Let's write down with respect to the grading X plus, X plus. Then I have X plus. Okay, let me do it in a way such that they will match up. Let's call this X plus, X minus. Yeah, this is better. X plus, X minus, X plus, X minus, X minus, X plus. And this is your X minus, X minus. Okay. I have simply written down all the generators instead of left to right, now top to bottom. This is 0, this is 1. Nothing fancy going on. Now I'm gonna draw the morphism in terms of the flows, but in the opposite direction. So I have a morphism from X plus to X minus, X plus. But now instead of the arrow going that way, it will go this way. I have flipped the arrow, so you're looking at the opposite category. Nothing fancy going on. So X minus to X minus, X minus, the morphism goes this way, but the flow direction is in the opposite, so it goes this way. This thing makes a flow category. Now it's a flow category. Now it can be an input in CJS, Cohen-Jones-Segal's construction, and it will give a topological space out like this, like magic. And homology of that topological space will be your Khovanov homology by the construction, because this machinery takes care of it. It literally gives you the Khovanov chain complex back. So that's the game. So let's look at the topological space, how it looked like, and I have chosen a very simple example just to demonstrate. For complicated nodes, the diagram becomes very complicated, and but this one is really simple and this is very hands-on, so we can do it really easily. The idea is for lower dimensional, for 0 is lower than 1, right? So you choose a lower dimensional cell for each of these generators, and higher dimensional cell for each of these generators, and attach the higher dimensional cells to the lower dimensional cells by using these flows as your attaching maps. That's essentially the idea. Let me show you hands-on. So for 0 dimensional, you have these cells. For X plus, so I'm choosing an interval because it's easy to draw, easy to manipulate, but you can choose an interval, you can choose a 2-disk, you can choose a three ball, doesn't matter. Whatever you choose, if you choose a 2-disk, it has to be 3 or 4. If you choose a 1, it has to be 2-dimensional. So just for that purpose, for drawing purposes, I'm just going to draw interval. But it can be 2-disk, 3-disk, it doesn't matter. Let's draw this. This is your X plus. I'm associating an interval to this X plus, and this is your X minus. Okay. Now the recipe tells you that you put all of these boundaries together. You let the interval for, in this case, this is your boundary. You collapse all of the boundary to a point. That's your attaching map. If I collapse all of my boundary, for this portion, I will get one circle, and for this portion, I will get another circle. Right? I collapse all the boundary to that point. Good. So this is what happens at the 0 level. Let's see what happens at the 1 level now. So this is your one-dimensional cell complex, or what do you call it, one scalita. Now, what about this 2-dimensional cell complex tells you it has to be attached to here, right? And the attaching maps will be dictated by these flows. So let me show you. Yeah, let me show you. For that, I think I use different color will be really good, but let's just see how much I can push. So for each of these generator, you attach a higher dimensional cell complex. I have chosen 1-dimensional here, so it makes sense to choose 2-dimensional here. So this is your X plus, X plus. It's really simple. Yeah, and once you choose, fix them. You can't choose 2, 3 like that. If you're choosing 2-dimensional, make sure all of them are 2-dimensional. If you're choosing 3-dimensional, make sure that all of them are 3-dimensional, like that. Good. Just like we had associated intervals over here, for the higher dimensional, I have associated higher dimensional cells for higher generators. That's it. Now the question is, how do we attach? For that, we need to identify this lower dimensional cell complex with this higher dimensional cell complex. So in this case, your X plus is sitting, so there is a morphism between X plus to X plus, X minus, and X minus to X plus. What you do is that you imagine this X plus, this generator X plus is sitting inside X plus, X minus. So this interval over here is sitting inside X plus, X minus, and X minus, X plus. And I don't know, let's draw this interval. This is your blue interval. Let's use some other color for that interval. Let's use red. And this interval X minus is sitting inside that X minus, X minus. Any questions so far? You have a question? All good? So wherever the generator goes, so X plus is going X plus, X minus. So I'm looking this copy in here, and this generator goes X minus, X minus. So I'm looking this copy over there. Now we will do the attaching maps. The attaching map goes in the following way. It goes in the inductive way. That's why the cellular structure is being preserved, and that's why the cellular chain complex is being preserved. Basically, you attach this portion of here to here, this portion of here to here, and rest of the portion you identify to the boundary. Same here. This red portion go to this red portion, and rest of the portion go to this west point. Same here. In here we don't have anything to worry about, so all the boundaries getting mapped to a point. That's what's happening. So if all the boundary of this x plus and x plus, let's use a different color. This is the boundary, right? Is getting mapped to a point. It is getting mapped to a point. Then what did you get? How did you get? You will get a sphere. It's a square. All of my boundaries getting mapped to a blue point. You get a sphere. Over here, this guy and this guy, they are matched, and this guy and this guy, these two are matched. So you'll get a picture like this. If I attach both of them to this interval, both of those portions are being attached to this interval. Now the idea is we attach everything to the boundary, the boundary of this guy to a point. Again, the boundary is getting mapped to a point. This entire boundary is getting mapped to a point. That will give you this picture. Let's do it here. I'll do it over the other picture over there. So the blue line, if I map everything to the boundary, the blue line, this portion and this portion will come around. It'll give you the circle. And it will give you the cylinder. Now, all of the boundary is getting mapped to a point that should give you that should also give you a sphere. Am I right? Am I getting a sphere or not? Yes, I'm getting a sphere. Yeah. So all of its boundary is getting mapped to a point, and over here it's also getting mapped to a point. That will give you a sphere. And if you can't see this, let me know. I will explain again. And for that guy, let me draw that guy, and I will take questions, and then I will move on. For that guy, this guy is matched over here. It's getting mapped to an interval, and rest of the let me draw that picture over here. So this guy is mapped to this interval over here, this portion of it, and rest of the portion, this boundary, is getting mapped to a point. So that will give you a disk. These two are mapped together, and it will give you a disk over here. Or from this picture. And these two are giving this picture. This is giving you this picture. Okay, big question. Why is Adi finally? one guy. So are these pictures clear? So yeah, and by the way, and as you do this process, this blue line is getting mapped to this guy, and now the boundary of this guy will be this guy. So this blue line becomes this blue line. This, I don't know, this. So basically, what you do, you can't see it here, but let me show you here. This is your one of the circles. This is coming from this blue line, and this is your red line. What happened is your red line got identified with a disk, it got filled in. Your blue line got a sphere, and to the point you got another sphere. So we got a topological space. This topological space is very simple. It's a wedge of two spheres. That's all it is. Right? It's a wedge of two sphere. Now, what is the reduced homology of two sphere? Right. Reduced homology of two sphere?
Z. 0. Z.
That's for RP2. S2 is very simple. S2 is even simpler than that. You're right. You get reduced homology. You get 0 at H0. You get at the 2. You will get Z, and the rest of the copies are 0. Because homology detects the hole, right? And it has just one hole, two-dimensional hole. So it tells you if you compute its homology, this is your Z, detect some Z at 2, at the homology level 2, and 0 elsewhere. Right? This is where I use the word stable homotopy. You will literally see why the word stable homotopy is coming in. It's because now let's go back over here. So this thing is not only any picture, this is the picture of your unknot with one twist. Let me see. This is the picture. Yeah, this is the picture I want. This is your unknot with one twist. And homology of this guy is, Khovanov homology of this guy is Z detects some Z at the quantum level 1 and -1, and at the 0th level and 0 elsewhere. We computed this sometime back in the beginning of the classes. So this is the quantum homology of this guy. So all it is, that thing gives you the homology if you shift this grading by 2. If you shift the homological grading of this guy, so this is your Khovanov homology of your unknot, but if you shift it by 2 on this direction, on the right, you will get it coincides with the homology of this guy, right? So let me show you what's happening. So this is your Khovanov homology of the unknot. This is your S2H S2. For S2H S2 telling me the homology for me is Z direct sum Z only at 2. 0 is elsewhere. I'm not writing 0 as at elsewhere. This is saying Z direct sum Z at 0. Cool. That means to match up, to say that this guy is isomorphic to this guy, I need to shift the homology by 2. If I shift the homological grading by 2, now it's at 2, not 0. Right? Now note that since Khovanov homology is a homology theory, I can shift it up and down as I want. For example, if I do Khovanov homology U at shifted 3, KH of U shifted at 3, it will be your Z direct sum Z at 3, 0 elsewhere. Similarly, I can shift the space upwards. I can always shift a sphere upwards. I can take it suspension. So suspension of S2 or its suspension of S2. Now this guy will have homology at Z direct sum Z at 3, 0 elsewhere. So the homology behaves nice under suspension, if you remember this. So Hi plus 1 of suspension of a topological space is isomorphic to Hi of X. Homology behaves nice with respect to suspension, but homology does not behave well with respect to your loop or desuspension. On the contrary, homotopy groups behave well with respect to your loop spaces, taking the loop. It does not behave well with respect to the suspension. That is the problem. For homology theories, you can shift up +2, +3, and you can shift down -2, -3. For example, if I do Z direct sum Z, this will be your at -2. Now I need to find a topological space that enjoys a negative dimensional hole or negative dimensional grading, for which you get the homology at -2, you get Z direct sum Z. There is no topological space like that. In topological spaces, you can always shift up. You can't shift down. In other words, topological spaces are not triangulated. So let's go back here. Problem with them to do homology theory, they are not triangulated. In other words, you can't shift down. To shift down, we use something called as formal inversion. That is, we make this suspension map invertible. And what we do is talk about spectra. That is at -2, so it has to be shifted by 4. So these guys, negative dimensional spheres, what does it tell you? This is your S-2, which is -2. It tells you homology of this guy. Z directs some Z at -2, here is elsewhere, if we follow the rhythm. But these guys, as topological space, have no sense. These are not topological spaces. These are spectra. So how should you think about spectra, at least for this class? I think I have introduced spectra, this K-theory class, and even one of my this lecture session is in one of the informal seminar. You simply think of spectra as your topological spaces where suspension is invertible. That's it. Where suspension is invertible. This is so how do you think about complex number? You think of them as real numbers where your x squared equals to -1, right? This is how you think about complex number. Rx where x squared equals to -1. Think about topological spaces where suspension is invertible in this analogy. So basically, you can desuspend, you can shift back. That solves the issue of forming an analogous space that respects your homology theory. As your homology shifts up and down, the spectra can shift up and down. That's it. That's all you are doing. And that may look confusing at the time, but after seeing it a few times, you get used to it. You may not understand as you are seeing it for the first time. Trust me, I did not as well. But once you start getting used to spectra, you'll realize that it's much, much, much better to talk about them when doing some theory analogous to homological algebra that involves homological algebra, for example, Khovanov homology or other homology theories, instead of spaces. The other benefit of talking about spectra is that you can take homotopy co-limits. And that feature unlocks another analogous definition for this doing Khovanov homotopy, where if you do not like all this geometry, you get to sweep all this geometry under the rug and compute it manually. And this is that manual process. This is the manual process. So what you do, oh, I'm so stupid. I erased that only diagram that I needed to keep, but okay. What you do, so out of these, instead of talking about flow categories, you think of them as functors. A functors form, in this case, (2⁻1) to something, that's something I am not defining yet. So what you do at the 1th level, you collect. So 1 is getting mapped to all of these guys. 0 is getting mapped to all of these guys. So this is the functor you want to build. So what you want to build, so you want to involve that information on your right-hand side using this functor. 2 to the power n to something. That's something I haven't decided yet, but for example, over there, 1 is getting mapped to x plus, x plus, x plus, x minus, x minus, x plus, and x minus, x minus. And 0 is getting mapped to x minus, x plus, x minus. This is what you want. At the 0 level, I have this information. At the 1 level, I have this information. So this is a set. This is a set. We really want, back of your head, we might want to land this functor inside the sets. But here is a problem. The problem is at the morphism level. If you look at the morphism, I don't have any morphism from x plus to x plus. I have morphism from x plus to x minus to x plus over here, and then x minus to x minus. So in general situation, we might miss some of the set elements. That means it's no longer a morphism of sets, right? Because we're missing some elements from the domain. And in some cases, the dual picture might happen. So one morphism that has one source can go to multiple targets. For example, this guy. For example, for this guy, we can have x plus x minus going to your x minus, and x minus x plus going to x minus. And this is your 0, this is your 1. If you reverse the arrows, you get this guy. One set element going to two multiple morphisms. That means that even if you call these guys your sets, we can't call morphisms as set morphism. Instead, the idea is to label this morphism as your set morphisms as well. So what you really want is this guy. Now, call this morphism, I don't know, ABC, ABC. This is this thing, this ABC is your morphism as a set. Now I get to choose what my source is, what my target is. This ABC has the source in x plus x minus, x minus x plus, and C has, these are all source. And C has the source in x minus, x minus. And target for A is your x plus, target for B is your x plus, target for C is your x minus. Is your target. So instead of thinking your morphism as set morphisms, if you simply think of them as sets, and you remember where they start from and where they end by literally assigning them a source and target to them, you have this information unlocked. That means what you really want to look at a category where the morphism look like this. Where the morphism look like this. A category where the morphism look like this instead of this. A straight arrow, a multi-arrow. These categories are called Burnside or category of the spans. And they have a rich history. They show up in many contexts. Using these correspondences, Grothendieck, I think, gave the first definition of the motif. Using these correspondences, you can do, with a group action, you can do some equivariant homotopy theory. But for now, what we really want to see is to capture that information in a functorial way. So as a functor, this much is good enough. So I didn't define this functor. This V will go to f of V, that is this Khovanov states. And your morphism will be a span. F of U to V is f of U, f of V dictated by the Khovanov complex. In Khovanov complex, let me write this down. Given any knot, you can always get this information of this. This information you can find any knot. If you take any knot as your input, you can get this information out just by writing down the Khovanov complex that we have been writing down. How much time do I have? Oh yeah, I have 10 more minutes. Okay, good. Then the idea is, so I want to sweep all that construction on the middle board under the rug, and I want to use this feature of the spectra and the homotopy co-limit gadget to build this thing out. So let me show you how to do that. So let me erase this board, unless you have a question here. So this is how you build a Khovanov. This is how you build a Khovanov functor. You can call it FKE if you want to call it. Then what you do is that you thicken this diagram out. This is your step one. Step two is to get the thickened diagram out. Build this functor. The paper that I'm following is Burnside category and Khovanov homology and cubes. In that category, they are first building the topological spaces in a convoluted way, and then they're lifting it to spectra. They are defining it a wage over the pullback and a product over the second term of the pullback. I don't know why they did that. Maybe, I don't know, to show off, I guess. I don't know. But let me give you the simplest description I could come up with to make your life easier. So what this category means, it means your two composable morphisms, UVW, F and G. Two composable morphism in the cube. In the cube. And this thing under the Burnside functor looks like this. F of U, F of V, F of W. Morphism from here to here looks like a span, so it should look like this. That's your morphism F of F. Morphism from F of V to F of W should look like a span, so that's your F of G. And composition of morphism, so composition of this guy with this guy is a pullback. That's the natural thing to do, obvious thing to do. If this is not obvious to you, it's simply because you are not really comfortable looking morphism like this. But if you get comfortable looking at morphism as two morphisms, this is the natural thing to do. This pullback is your composition. F of G compose F. And what they do, these are your objects over here, this UVW, FG. They assign it to sphere spectra. That means if you can't think of sphere spectra, simply think of S0, where the wage is varying over the cardinality of this guy, F of G compose F. So this is a set. This is a set. Pullback of two sets is also a set. It's a subset of this Cartesian product. Subset of the Cartesian product where these two arrows are matching over here. That's literally your pullback. Now what I'm doing, I'm assigning some wage of the spheres based on the cardinality of that set. That's all. So an example would be this example we'll see what happens over there. But this is what you're doing. The interesting thing is that what is the morphism? And I won't explain the morphism because that will take so much time and I don't have that much time. I do have the diagram drawn over here. And if you do want to understand sometime, let me know. I'll be happy to talk. A prime, G prime. The problem is morphism in this category, they look a little different. A morphism, so this is an object in this category, this is an object in this category. Suppose we want a morphism from here to here, that morphism look like this. These two side arrows are going in the right direction. And this arrow, this middle arrow, going in the opposite direction. These red arrows are morphism in this category, from here to here. And I claimed, but I don't prove, that will induce S0. A morphism to this. So this is how I build the functor. I take my object to this copies of spheres, take these objects, all the objects are same, to the copies of sphere, and the morphism induce the morphism on the which copies. In easy way, how would the morphism look like? So imagine your one sphere. This is the property of the sphere spectra. In your category of the sphere spectra, your co-product and product coincide. And that means the construction that I'm giving you is equivalent to the construction you'll see in the paper. And but anyway, so what I want to say that so there will be only two cases when this morphism is interesting. when one sphere splits into two sphere or three sphere or dot dot dot, that's essentially your fold map composed 2 or 3 times. Sorry, not fold map, pinch map. So one sphere getting into two sphere like that, or 3 sphere, depending on how many copies of the sphere. This is one interesting map. And the other interesting map is this guy. Bunch of copies of the spheres getting mapped into one sphere by using the fold map. That means that this and this 2 copies are matched over here, and this copy is matched over here, this copy is matched over here, like the fold work map out of the co-product. These 2 maps are the only interesting maps from here to here that you will see. The rest of the maps are identity, so they will cancel out while taking the homotopy colimit, which you're going to see next now. All the rest of the maps, these 2 are the interesting maps. The red arrow, interesting. Rest is identity. So they canceled out in the next step. And this is the next step. Note that I'm not doing a bit of geometry while defining this, but still you will see something fascinating. And what you do, so this gives, oh, okay, I did not say one thing. So what does this plus means? Plus means that I'm being pedantic here. I could avoid this. Plus means that you have another object which enjoys a morphism from this guy if W is non-zero. If the last term that you see, it's ending over here, it is non-zero, then that is the only time it enjoys a morphism into the star. And star is an extra object that is denoted by the plus over here. If it looks complicated, don't worry about it. At least not for now. And the next thing you do is to take the homotopy colimit of this diagram. You take the homotopy colimit of this diagram. If you don't know what that means, simply think of taking a colimit of a small diagram. If you don't know what it means, colimit, simply think of taking a fancy union. However you want to think about it. So homotopy colimit of this diagram will be an actual raw topological space. This will land in spectra itself. So again, think of spectra as a topological space where the suspension is inverted. So this will land in a topological space where the suspension is inverted. And then what you do, to match it with the Khovanov homology grading, you desuspend it with respect to your negative crossing. And honestly, I really don't like to call this guy, but essentially what you get up to modulo some, modulo some suspension, because I really don't want to confuse you introducing more symbols, modulo suspension. You get your exact construction back, this guy back. If I have some time, I can show you how to get that back, and we'll stop. You have some time, like 2-3 minutes. It's 14. 4:18. So we have 2 more minutes, right? So I can show you. So let me show you on hands-on approach on how to get this, how I will get the same information out of this colimit, and then we will stop. So let's follow the steps. Your first step is to form the functor from 2 on to one side by using that information. That means your 1 is getting mapped to 1 plus plus, 1 plus minus, 1 minus plus, 1 minus minus. 0 is getting mapped to 1 0 plus, 0 minus. These are your sets. And your set maps are your ABC. This is your A, B, C, where A is connecting these 2, B is connecting these 2, C is connecting these 2. Good. Now what you want, this is the first information you get out of that knot. Second information you want to build is to build the thickened category, the 2, 1 hat plus. So that looks like something like this: 1, 1, 1, 1 to 1 to 1 morphism. They're composable morphism, but I really don't want to introduce more notation, so just call it 1, 1, 1. And then we have 1, 1, 0, composable morphism, 1, 0, 0, composable morphism, 0, 0, 0. And if you follow that convention of one arrow going in the opposite direction, you get unique maps in these directions. With star, which enjoys a morphism, if the last object is ending in that ends in is non-zero, that is only this object. So you get a unique morphism over here. So this is how your 2, 1 hat plus looks like out of that information. Now what you do is to associate the weight of the sphere spectra. So in this case, this is your f of 1, f of 1, f of 1. It's all bijection, it's all isomorphism. So what you will get is 4 copies of these guys. I'll be going really fast now, but let me know if you have anything. All spheres. From here to here, so 1, 1, 0. So for 1, 1, you will get only these guys, and for 1, 0, you will get A, B, C, and their composition. Since these guys are composition is like so what I want to do is show you this one. Let me show you f of 1, f of 1. This is your f of 1 to 0. This is your f of 1. So these are all bijection, all bijection. So in the pullback, what you get is this guy back. The pullback will be isomorphic to f of 1. That would give you S wedge, S wedge, S. Similar logic will give you S wedge, S wedge, S. And this will give you 0, 0, 0 is this guy. So it will give you 2 copies of spheres. Now here is the fun part. The fun part is you can split this diagram with respect to your quantum grading. Note that all these attaching maps, all these morphism lie in between the same quantum grading. For example, here the quantum grading is 0 or shifted by 1. It doesn't matter. For now, we'll call this 0 plus 1. 1, 1. Here the quantum grading is minus 2, but shifted 1, minus 1. And here the quantum grading is 2, 3. Here the quantum grading is 1. Here the quantum grading is minus 1. So the morphism only exists in between same quantum graded objects. That's why the morphism exists. That means your maps exist between same quantum graded objects. And that's the power. So this is your 3 sphere. So this is your 3, this is your 1, this is your 1, this is your minus 1. This is your, I have using these morphisms. So this is your 1, this is your minus 1, this is, sorry. So this is your 1, 1, and this is your minus 1. This is your 1, 1, this is your minus 1, this is your 1, this is your minus 1. So you can split this diagram with respect to your different quantum grading. You will get 3 diagrams. We draw them quickly and we'll be done. This is your S at 3. Nothing goes to, so 3 is not getting mapped to anywhere in the 3 graded object. There is no 3 graded object. That means it is getting mapped to a point. Over here, something interesting will happen. S wedge S. This is getting mapped to S wedge S. This is getting mapped to S wedge S. This is getting mapped to S. This is your identity map. This is your identity map. It will take some time to get used to it, but it will be identity map if you just look at it. And this is the interesting map I was talking about. This is your fold map. You'll see your fold map over here. And the last one is your minus 1. So this is your star. S, S, and the minus 1. This is your 3. This is your 1. This is your minus 1. S, 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 S. So all of these maps are identity. Now here is the trick. Okay, this guy, so homotopy colimit of this guy will give you suspension of the sphere. How you do homotopy colimits? You do S cross I, and you identify this upper part with the point, lower part with the point. That means you get the suspension, right? I identify this with the point and this with the point. This is how you get the suspension of the sphere. Here is the interesting thing will happen. I will keep it in the end. And this is where, this is where the trick I will use. So everything is identity. This part is fully identity. And if I have identity in the co-limit system, I get to cancel them out. So you will get a point. Same trick here. Since I have identity in the co-limit system, I get to cancel this guy out, this guy out. I will only have this guy left. Now the question is, what is the homotopy co-limit of this guy? What is the homotopy co-limit of this guy? For that, what you do, you get the same idea. S wedge S should be in the middle. You look at its cone. And the top surface you identified with a point. So all of this is filled. Getting identified with a point means I'm filling the top surface, right? And over here, I'm using the fold map. So that means this side is getting mapped with this guy. That's the fold map. Now, if I do that, so basically top surface is filled up. This side is getting mapped with this guy. You'll see a sphere. If you just look at it, this side is fully getting mapped to this guy. If you draw the diagram, coming in, you'll see a sphere. So you started with S1, you get S2. So what you are getting is suspension of the sphere. And these are all your weight summands. So what you get is suspension of sphere, weight suspension of sphere. And you have to do some grading shift depending on the crossings. And if you do the grading shift, for example, here we have one negative crossing. That was your one knot with one negative crossing. So what we do, we shift it by one, the backward, you get sphere spectra with sphere spectra. And homology of this guy is your C direct sum Z, and only at the 0th level, rest is 0. So there you go. So this is your analogous way of building the spectra without using any geometry, whatever you prefer. But this is more algorithmic. That's all. Adi is there. Do you have any question? Adi? Hopefully. Oh, you're here? Okay, good.
So like this is up to a homotopy you said, right? Like S2, the last construction?
Yeah, I knew. So in the last construction, so if you look at the paper, yeah, this is a good question. Let me erase this. Is this more on? Yeah, nice. Thank you so much. You asked this. So in the paper, you will see this thing. So they are mapping this UVW to wedge of A belongs to the first pair, product of B such that your S of B equals to T of A, sphere spectra. Okay? And the map that they use to go in between product is your diagonal map. If you look at the paper, are you with me?
Yeah.
If you look at the paper, this is exactly the same information they're giving you. Now, this is the feature of your spectra. In your world of spectra, up to stable homotopy, your co-product and product coincide. It's additive. Co-product and product coincide. So you can replace this guy by wedge. That means that you can simply run this over all your elements of the pullback. And the morphisms, they also need to be matching, right, with the diagonal map that get matched because this diagram commutes. So this diagram for your topological spaces anyway commutes. It's nothing fancy. This is your pinch map, this is your diagonal map, and this is your cellular inclusion for all your spheres. But the point is, in your spectra, in your stable homotopy, this is actually a stable homotopy equivalence. This guy is stably homotopy equivalent to this guy. So that means up to stable homotopy, you can replace the diagonal map by the wedge map.
I see.
Up to stable homotopy, you can replace that by that map by wedge map, and that means all of these maps are valid. So this is a formulation that I came up with. You can literally write that down, and all of the math will work. Yeah.
Okay. And the cancellation with the identity doesn't matter the order in which you thought the arrow.
No, the cancellation of the identity doesn't matter. So what do I mean by cancellation of the identity? That means that you identify this entire thing with just this thing. You
Oh, okay.
identify this entire thing by just this thing. That's what I mean. Cancellation by the identity, it means you take the entire part out. That's what I mean. By cancellation, I don't mean you take both of the part out. I mean, if you that thought like that, yeah. It means here the same thing as well. You get to take this part out, you get to take this part out, you get to take this part out. Now this is the homotopy co-limit of S going to a map out of the morphism, so it would be a point. Does it help?
Okay, yeah. Thank you.
Yeah.
That is a good talk. Thank you.
Yeah. See you in the next semester.
Yeah, see you.